Hi, this is Kent, and I am here to present joint work with Chandra Chekuri of University of Illinois called Isolating Cuts by Submodularity and Faster Algorithms for Connectivity. So I'll start with the concrete, simple problem of undirected edge cuts and some work that motivates ours. So here you have an undirected graph as positive edge weights, and the goal is to disconnect the graph by removing a minimum weight set of edges. So on the right, these red edges will give you the cut, and there's already a randomized nearly linear time due to David Carter, but there's been recent interest in trying to get a deterministic algorithm that's competitive. So Lee and Panigrafi showed that you can give a deterministic reduction from global min cut to logarithmically many max flows via this very interesting idea of isolating cuts. And as far as de-randomizing Carter's algorithms goes, this was actually improved in follow-up work by Lee, who more directly de-randomized Carter's algorithm. But we're really interested in this idea of isolating cuts, and so the starting point of our work is trying to generalize this and explore this idea beyond this setting of undirected edge cuts. So as an example, consider hypergraph cuts. So hypergraph is like a graph, but an edge may contain more than two vertices, and you can define connectivity and cuts naturally as an extension. And the goal is to find a minimum weight cut of hyperedges now. And this problem you can solve with max flows and many max flows, but you can do better. So the state of the art is roughly the input size times n. Okay. As another example, generalizing or going beyond edge cuts is vertex cuts. So here, rather than edge weights, we have vertex weights. And I want to find a minimum weight set of vertices whose removal will disconnect the graph. So this too can, of course, be solved in polynomial time with max flow. And the state of the art for weighted graphs is better, is MN by Hensinger, Round, Cabal. And I'll just note that there's been lots of recent results, especially for unweighted or approximate versions of this problem. Okay. Yet another version of connectivity is element connectivity. So here you have an undirected graph, and the vertices are partitioned to two types. You have terminals and you have non-terminals. And having established terminals, an element is any edge or any non-terminal vertex. So those are elements. Now for two terminals U and V, the element connectivity is defined as the maximum number of element disjoint paths from U to V. But terminals you're allowed to reuse many times, as in this picture where W is used twice. The global element connectivity is the minimum pairwise element connectivity over all terminal pairs in your terminal set. You can solve this, of course, by trying all pairs, but you can actually do better, and in roughly the number of terminals, that many min cuts. Okay, so element connectivity, for those who are interested, have actually a lot of interesting applications in network design and elsewhere. Okay. Now, the final setting I'm going to introduce is symmetric submodular cuts. So here the input consists of a symmetric submodular function, f. So it takes some subset of elements and outputs a value. We say that f is symmetric if f of s is always equal to the f of the complement of s, s bar. Okay? And f is submodular means f exhibits decreasing marginal return. So if I'm looking at f of a plus j minus f of a, so this is sort of how much f goes up when I increase j, and I compare it to how much it goes up when I add j to b, if A is a subset of B, then the marginal value of J will be greater to A than to B. An alternative equivalent definition is to say that for all sets A and B, f of A plus f of B is at least f of A union B plus f of A and B. And so for this kind of problem, we're assuming we can access f via an oracle, and we let n denote the number of elements. Okay. And the problem is to minimize the value f of s over all non-trivial sets. So S can't be the empty set, and it can't be all the elements, but otherwise I want to minimize f of s. This generalizes undirect edge cuts and hypergraph cuts because those cut functions are submodular function of the vertices. But importantly, it doesn't generalize vertex connectivity and doesn't generalize element connectivity. Now this problem too, you can solve in polynomial time. You can reduce it to polynomially many submodular minimization problems. And the state of the art requires n cubed evaluation oracles. Okay. All right, so having established these problems, let me introduce our results. So really our first line of results is improved bounds for all sorts of these problems. For undirected vertex cut, we get better approximations, and we get better exact algorithms for hypergraph, element connectivity, symmetric submodular cuts. But really, I think what was interesting to me is trying to kind of understand the isolating cuts argument and try to find the right place for it. So identifying the right combinatorial abstraction where this isolating cuts argument can be applied much more widely. And then after that, we actually found out that even after getting isolating cuts to sort of work in these more extended settings, there's actually more work to be done. And so there's this sort of interesting design space, algorithmic design space that comes after the isolating cuts stage that we sort of help develop and expose. Okay. So now to be able to explain these ideas in greater detail, let me try to quickly review the isolating cuts argument. So okay, let's say we're doing some undirected graph cut problem. So we have some graph, and the minimum cut maybe looks like this. Okay. And let's say we knew how many vertices are on each side of the cut. So maybe there's k vertices over here, and there's n minus k vertices over here where k is less than n over 2. Okay. So so how does this relate to isolating cuts, and what are isolating cuts? So if I knew that there was k vertices on each side, which we can guess, let's sample each vertex with probability 1 over k. Okay, and with constant probability, I only get one vertex from the small side, and then maybe a lot more vertices from the large side. But the point is that I have one on one side and everyone else on the other. Okay. That means that our cut is an example of an isolating cut in the sense that it isolates this one vertex from all the other vertices. Okay, that's what an isolating cut is. So now by just sampling, assuming we can guess k, we've reduced this global minimum cut problem to isolating minimum cut, where I just want to split off one sampled vertex from the rest. Okay, so now how do you solve isolating cuts? What makes isolating cuts easier? Okay, so here's the algorithm by Lee and Panagrahi. That's really elegant. So we've sampled some set of vertices, and my goal is to rip off one from the other. Okay, but I don't want to really kind of do all pairs type of computation. So one idea is to repeatedly split this set of terminals, this sampled set, into two halves. Okay, and then find the minimum cut between them. So you make some super source and a super sink, and you compute the minimum ST flow. Okay. So that gives you one cut somewhere in between. And okay, but then you do this again and again. So you find a different partition in half, maybe like this, and you find the minimum cut between them and so forth. So you keep partitioning until you guarantee that every pair of terminals is separated at least once. And so you only need to do this log n times. Okay. And so, yeah, so maybe here would maybe be another part and so on and so forth. So now for each vertex t, each of these sampled vertices t, we can look at just the intersection of the sets that contain it. So here we call this U sub t. And so these intersections, once you do enough AIBIs, will be disjoint. Okay. And so the key argument really comes here, uses the symmetry and submodularity of edge cuts to argue that if I just look inside this region, I will find the minimum cut that isolates that vertex from all the other purple vertices. Okay, so not only do we partition a graph, but now we only have to look inside each part for each vertex. So for each of these terminals, then you take everything else and you contract it to a single vertex. So maybe you're looking at some t and there's some region, and you've taken everything else and you've shrunk it to a single vertex, and then you find the minimum flow to get the cut. Okay, and so what's making this work? Because these U sub t's are disjoint, the total size of all these contracted graphs added up is roughly the size of the input graph, which means that the combined running time of these flows is really just like one max flow on the input graph. Okay, this is very clean. So what were the key points then towards getting this better running time? Symmetry and submodularity of graph cuts lets us sort of uncross these log n partitions and cuts and argue that these intersections will still contain what we really need. Okay, so symmetry and submodularity is really important. And the other part that comes out of graphs naturally is that when we look at the intersections and these subproblems, we really cleanly partition the input. So the fact that the U sub t's induce subgraph that are really edge and vertex disjoint means that second stage of max flow problems is also very fast. So the meta question then is sort of how robust are these arguments? What happens if I take away symmetry? What happens if I take away partition? Can we still get something useful? All right, so then let me present two of these extensions. So one is hypergraphs. So hypergraphs, as mentioned, are still symmetric and submodular, so some kind of uncrossing argument goes through. The issue comes in that partitioning stage. So if we do the uncrossing on hypergraphs, we will sort of split up the vertex set into different parts. All right, so you will partition the vertices, but a hyperedge, in the input graph can contain vertices, many vertices, and so it can span many parts. And so when you look at these subgraphs, you have all these, you create a lot of hyperedges total across the subproblems. So the fact that a single hyperedge can appear in multiple of these subproblems is going to blow up the running time when you start applying max flow. Okay. All right, so another basic example then comes in vertex connectivity. So So vertex cuts, first of all, are just not submodular from that f of s point of view. So maybe here's like a vertex cut. Okay. Which has maybe two parts on each side. I'll call this A, and I'll call this B. So this vertex cut is equal to f of A, and it's also equal to f of B if f is giving you like what is the size of a vertex cut surrounding that set A or that set B. But A is not, of course, equal to the complement of B, and B is not equal to the complement of A. So this is not a symmetric submodular function. Okay. And just looking ahead, even if you could somehow argue that you could do some uncrossing, we'll see that in the subproblems, an issue that arises that these boundary vertices have to appear in all the subproblems for the sake of correctness, and so you're no longer partitioning input graph again. So partitioning is also an issue for vertex connectivity. Okay, so yeah. What do you do when you don't have symmetry, and what do you do when the decomposition isn't so clean? Okay, so let me take a half a step back and try to understand how these problems are related. We started from undirected edge cuts where everything works nicely. This can be generalized to hypergraph cuts, or even more abstractly, symmetric submodular cuts. Another problem of interest, of course, is vertex cuts, and 1 plus epsilon vertex cuts is captured by element connectivity. And so there's some sort of question of, okay, is there any way to sort of unify and understand all of these problems at once from a clean, comprehensive perspective? Okay. So this is where we bring in some of this abstract framework. So there's the generalization happens in two places. First is by introducing these crossing lattices. So rather than looking at sets, I'm looking at pairs of sets, pairs like A, B for the vertex cut. So a family of these set pairs is a crossing lattice if it's closed under these crossing operations. So the meet will take the union of the first component, intersection of the second component, and the join will take the intersection of the first component and the union of the second component. So, a nice motivating example then is vertex connectivity again, right? So the natural thing is to say, all the vertices on one side, that's my set B, A, and all the vertices on the other side is my set B. Of course, A and B are not complements of one another. Okay, but that would be sort of a feasible set pair in the crossing lattice that helps model vertex connectivity. And if you work through it, these crossing operations or uncrossing operations, the meet and the join will actually preserve vertex cuts. Okay, and also using vertex cuts as an example, we'll say this family of set pairs is symmetric if I can always reverse the pairs and get something feasible. Okay, so that's one thing, is to sort of expand out from focusing on f of s to f of two different sets, which are, for the case of vertex cuts, representing opposite sides. The second generalization comes from an f and looking at bisubmodular functions, which is sort of saying, submodular defined over this kind of lattice. So f of this set pair x plus f of this set pair y should be at least the meet and the join in the sense defined above. So that means if you kind of, in some sense, give me one set pair describing one cut and another set pair describing another cut, and I look at the two cuts that arise from uncrossing, the meet and the join, the original cuts should be at least the uncrossed cuts. It's also important for the argument to have symmetry in this sort of bi-submodular sense, which is just that the reversed pairs have the same value. Okay, so in this sense, we can incorporate that semi-asymmetry of vertex cuts as sort of but still symmetric if you look at two sets at a time. And so this is actually a good framework to understand all these problems at once. It'll generalize both element connectivity and symmetric submodular cuts. So sort of the Metis theorem we developed is to show that the uncrossing argument can be extended to this symmetric by submodular setting over the symmetric crossing lattices. With some care. And therefore, this isolating cuts approach does extend to element connectivity, and via element connectivity, one also gets vertex connectivity. Okay, so that addresses this obstacle from the uncrossing argument when you don't have symmetric submodularity. But I mentioned there was another problem that happens in these problems where the graph doesn't decompose nicely. So let me demonstrate by using vertex connectivity as an example. What is the problem and what is one way to get around it? So when you do isolating cuts, you'll get this, the intersections will give you some kind of partition of vertices, as well as a bunch of separating vertices, some kind of boundary in between them. Okay, and so what happens in the subproblems then is that a single subproblem, you keep the partition, but you also have to keep the boundary vertices attached to some supersync. And so as a result, the separating vertices start appearing in multiple subproblems. Okay, so even though the edges are essentially disjoint across subproblems, the vertices can repeat, in particular the separating vertices can repeat. And so the sum of vertices over these subproblems can greatly exceed the number of input vertices, which blows the whole exercise of trying to do things fast. Okay, so so now working with this problem, here is maybe one kind of argument to address it and salvage the isolating cuts approach to some extent. So non-boundary vertices, so the vertices are inside these components, they're still partitioned across subgraphs. And if a subgraph has only a small number of internal vertices, then we show that you only have to use short augmenting paths to solve the corresponding flow problem. So blocking flows becomes very good. Okay, now what if there's a lot of internal vertices? The blocking flows isn't really getting you anything. That turns out to be okay because, by sort of Markov type argument, there can only be a few graphs with way larger than average L. And so we'll just, we'll run a full state-of-the-art max flow algorithm for each of these limited number of subproblems. And then balancing on L gives some better running time than if you had not done anything and just run max flow. Okay, so this is supposed to just sort of be a flavor. Other arguments, but sort of at a high level, these combinatorial arguments that are exploiting imbalances, looking for interesting trade-offs, they give other running times for vertex connectivity, as well as other problems. Okay, so let me then conclude. To recap, we get these better running times for a variety of basic combinatorial problems. But really, I think we sort of explore and put forth an abstract framework that extends isolating cuts to many more combinatorial problems, and we sort of identify that there's some stuff you could do that goes past just isolating cuts that can get you substantially better algorithms, and I think this is the place that still welcomes new and better ideas. Okay? All right. Thank you.